the last part we poked fun about the silent oscillator, and today let's look into the square oscillator. It's located in the test folder, so open it up and let's get started. Since this is a simple oscillator, let's just go through the structure piece by piece. First of all, we do have an include over here. We are including user oscillator.h. That's an include file. That's important for all the definitions in here. We will look into this one when we are explaining the waves oscillator. Right now, let's just say in this file. So first of all, as you can see here, I've got some wigglies under the name over here. The problem here is that there is some kind of bug with VS Code. So to alleviate this, I need to include this type definition. The rest seems to be working, which is strange, but that's how it is. All the other types would have been working, but the uint32 is not working. Let's take care of those types later on. I think that's another layer of complexity that we do not need right now. So that's the file that contains the complete oscillator. So the oscillator gets initialized at some point in time where we put in some variable default values, and then with 48 kilohertz, the oscillator is getting called by the synthesizer continuously to fill out the buffer, even if there is no note presses. So if there's a note press, note on or note off, you will get that info and you can restart your waveform, but the cycle is gonna get called all the time. All right, so the cycle doesn't get a lot of information when you are getting called, so that's the callback here. And you do get a few of the parameters, and you do get the buffer address, and you get the number of frames that you need to write, but that's all. You do not have any kind of stateful information in here. And if you just want to look into the type definition in here, that's in the user oscillator part of the header. Here you can see what parameters the oscillator cycle function is getting passed to. So first of all, the amount of the LFO for the shape, then the pitch of the oscillator, the cutoff frequency of the filter, and the resonance of the filter, and that's basically it. So that's the information that you get passed. And by the way, as it currently seems, the information returned in cutoff and frequency is not used at the moment. So this is what you get here. So you will be able to find out at what pitch you are and what LFO value is gonna get used. However, there is no way to put down some state in here. But as we know, we will need to have some kind of state. So what you do here is you just define yourself a state variable. The variable is actually here, but it's the definition of the variable because we will have multiple values that we need to store. And the most important part for a oscillator is the phase accumulator. That's the part in here, where you basically remember where in the cycle of a waveform you currently are, and then an increment per sample. That's of course dependent on the pitch of the oscillation. So if I just show you here one period of a sine wave, then this would be the complete period, and you can think of the phase as the distance from the origin down the complete cycle, and then after here not continuing on with higher numbers, but then returning back again to 0. And for the sine wave, we can do this as angles from 0 to 360 degrees or from 0 to 2 pi. And this is what is typically used for analog signals. However, since we are using a synthesizer, the phase is going to be normalized from 0 to 1, which makes it much easier to calculate with. And of course, this is going to be a float value. So we go through all of those points from left to right, and the phase is going to increase. And let's say that this is our W0 here. That would be a step increment. So for each sample, we would jump one phase increment to the right but we need to remember where we stopped, so that when we return back to the next call of the oscillator cycle, we know exactly where we stopped, so that we can continue incrementing at the same pitch. So this is why we need to remember the phase. Sometimes this is called the phase accumulator in DSP terminology, and that would be the phase increment, the W0. Duty and angle is for the pulse modulation. So if you look into a square waveform, I've just drawn one here. It's not easily detectable. So we are starting at the origin, and at the origin we're returning the value of -1. And then after 50%, we are switching back to 1. And then after half a cycle, we are switching back to -1 again. And since this comes from electronics and electricity, we call the load cycle or duty cycle the amount or the percentage of the positive value in relation to the complete wave. So this is right now, it's 50%. So if we put in here like this, so this would be 70% negative, but only 30% positive. This would be a duty cycle of 30%. So that's the duty cycle, and the angle here, this is just for the specific oscillator that the guys from KORG have written. That would be the decay in samples when instead of going straight, the waveform would go downwards. So this is how they implemented the whole thing. And then we have the two LFO state variables and also some flags. The flags are there to remember what happened when the oscillator gets in different states. So for example, when node on is played, we do get a reset, and we store this in our flags because the node on, off, and parameter callbacks are independent of the cycle callback, and they could be potentially called in parallel. This is why we need to handle this with a specific flag that will get handled after the next cycle is getting run. All right, so this is our state of the oscillator. So this is where we remember what is actually happening in the oscillator while different calls, multiple calls to the oscillator cycle are getting executed. We need to remember stuff, and we put it in here. This enumerator just enumerates our flags in here, and this oscillator basically has just got a single flag, which is called the reset flag. The terminology here is a typical C and DSP terminology. This basically just means 1. That's about it. That was the type definition for our state. And here, this is the actual variable. It's a static variable. This means that it's going to be defined once. You can call this a singleton if you like. So for the complete execution environment, there is only going to be one of the state variables. Now I hear you say, but what if I have multiple voices? How can this work that we just have one state if I do have 4 voices? Shouldn't we need 4 states? Yes, you're right. However, per voice, there is one processor running. So this code is going to get installed on a single small chip that is creating just one voice, and in that way this is going to be a static, a global variable that is not going to interfere with the other voices. Okay, so now let's continue. The oscillator init callback is getting called when I load the waveform. It gets 2 parameters. One is the version of the platform, and one is the version of the API. And when we will be handling different versions of the platforms and the APIs, this is going to be important. Right now, that just doesn't matter. What the programmers of this file did here is they are, of course, initializing the state with some initial values. We do not have an increment yet because we don't know at what pitch the oscillator is going to play. We do also begin with the phase of 0. The duty cycle is going to be 10% as a starter, and the angle is at 0 currently. You can see here that we are using float variables and float constants. It's very important that you remember to put down those constants as a float. And the reason for this is that the processor is optimized for running float commands very quickly. In order to support you with that, I have added a flag for the compiler, and this is in here. I have added a warning. We should get some warning when there is a promotion of a constant to double, or if there is a float conversion. So this is going to help you when you will be forgetting a f behind a constant here. Because if you do forget it, you will put down the constant as a double, and then it's going to get converted, which is going to cost you a lot of cycles. Do remember that this function here, that this call here is being called very frequently, and we need to fill out that buffer sample by sample at 48 kilohertz. Of course, this is a buffered call, so we will get called for multiple of frames at once. But still, we do not have a lot of operations per second, so keep that in mind. Also, the flags are gonna get set to 0, which means flags none. There is nothing to be done to the oscillator during the oscillator cycle. As I said, the flags can be used by the other callbacks to give back some information, to store it in here before the next cycle is gonna get and fetch them. So now we have got oscillator init completely understood, I hope at least. The next callback is the oscillator cycle callback. It gets 3 arguments, and as we already saw, and I'll just call that again, I'll just open that again. As you can see here, this is our type for the first argument in the callback. So we will get the shape LFO amount and the pitch and the cutoff and the resonance. All right, so this is what we get over here. Then we get a pointer to an array of 32-bit integers. So this is the output of what we will be returning to the synthesizer. And that's the amount of frames that is gonna get called. Okay, so now let's begin with the first cycling. So get the flags from our state into a temporary variable and reset the flags to none. So if there is any flags being set from other callbacks, reset them so that we will have no flag for the next run. Then get a conversion done from the pitch of the parameters that we get passed. So in the parameters we get passed a pitch, and this is referencing that pitch variable, and the pitch is getting split up into 2 parts. The first part is the actual note, the MIDI note, and the second one is the pitch modulation. Now, if we look into this specific function here, you see the documentation says get a floating point phase increment. So we get a phase increment for a given note and some modulation, that's the defined part of the pitch, in the range of 0 to 151 and the modulation in the range of 0 to 255. So we will pass the pitch and the fine pitch to this function, and the function is gonna yield a phase increment that we are going to store in the state variable W0 and also into W0 in the local scope of the function here. In the next line, we do check if there is a flag reset being indicated in our flags variable. If it is, this means that we should reset our waveform back to 0. So if our phase accumulator is, for example, at 0.6 or 7, reset it back to 0 because we want to restart with a new node, and a new node should always start at the phase of 0. So that's a if then else statement in C. So that's a ternary operator here. This is the check. This is what is in the if. So if the flag reset is set, then return 0. Otherwise return the phase from the phase accumulator and store this in our phase variable. Then get the duty and the angle from our state. Now fetch the parameters LFO amount and convert it. So the LFO shape amount is getting set by the user, and this is the returning value over here. So what we get is basically a value from the LFO and how in the amount and how it modulates our shape waveform. So you can configure this in the menu of the synthesizer if you want to modulate the shape of the multi-engine with the LFO. And if that's the case, this is the value of the LFO that is going to get passed to ourselves. So now we need to convert this. And the conversion here is from a fixed point, that's the Q, fixed point 31-bit to floating point 32-bit. So for some reason we are dealing with floating point only in the oscillator here. And the values, however, are passed to ourselves in the fixed point. So we get the fixed point from the synthesizer, and we convert it to floating point, and we store this in our state, and we store this in this LFO variable. In the next line, we are setting the LFO amount in condition to if the flag is going to get reset. If it's reset, set it to the LFO amount that we are getting from the synthesizer. If not, take the LFO amount from our state and put this in the LFOZ variable. Then compute the LFO increment, which is the difference between the LFOZ and the LFO divided by the amount of frames. So this means per cycle of a single sample. All right, now we have all the variables set up. Now let's go into the actual loop that is going to fill out our buffer. So as you can see here, our buffer is actually a Q value, so means it's a fixed point pointer to a buffer. And let's put this into, let's convert it to that, and let's put it into the variable y. All right, so we get our pointer initialized to the beginning of the buffer. And we also compute the end pointer. So that's the end of the outputs. So, and of course, if that's the beginning of the buffer, then the beginning plus the amount of frames is going to yield us the end address of the buffer. Now that's a for loop. This could easily be a while, because this is actually a while loop. So no condition here, no increment here, and you just get a comparison running. So as long as y is not equal to y underscore e, so as long as the current pointer to a output sample is not at the end, continue the loop. This is a bit dangerous because if you increase that pointer with 2, this loop is not going to end. So basically that's a very bad syntax over here. Much better would be less than or equal, but let's not take care of this right now. Now in the loop we are computing the value of the duty cycle. It's called PWM over here, by looking into the duty cycle that was set as a variable from the state over here. So this was 10% at the beginning, plus the amount from the LFO. But then don't let the value, the result over here, go out of bounds of 0.1 at the low end and 0.9 at the high end, and put this into PWM. Now this is the actual oscillator here for the square wave, and its result is called the signal sig, and it's also a if then else statement. So if the phase minus PWM is less than 0, and we will see when this is the case, return 1, otherwise return -1. And the results of the signal should be in the +1, -1 range if you want to have a clean waveform. It's not going to clip if you do otherwise, but it's not going to get the same waveform if you do so. So what this is doing basically is returning 1 if the phase is less than the PWM amount, and -1 if it's more than this. Now in the signal result we either have a +1 or -1, which is exactly what you would expect from a square or a pulse modulated waveform. And this is what we would store into our buffer. However, since here this is a angled oscillator, so if the angle is not 0, angle is actually a variable that can be set using the shift shape knob. So you press shift and then you turn the shift knob of the multi-engine, and in this way you can modify the angle of the oscillator. And the shape parameter, if the user turns the shape knob without the shift button, is modifying the duty of the pulse width modulation, and it's getting compute by taking the value from the synthesizer parameter, which is this one here, taking it and multiplying it by 0.8. So since the value is going to be in the range from 0 to 1, multiplying it by 0.8 will get you a value of 0 to 0.8, and then you add 1 to this. So the end result is going to be a duty variable from 0.1 to 0.9, so from 10% to 90%. This is how you limit this. And if you want to see how this works, what you actually get is a value that is a value from 0 to 1023. And you need to convert this to floating point. So that's the conversion over here. That's an efficient conversion. So dividing this by 1023. Okay, so how do you know which parameter has changed? Well, you get this in the index argument. So you switch in terms of index, and then you find if there is a specific parameter change, and if there is, react accordingly. Okay, now let's go back. Now we found out what the duty cycle and the angle is. So the angle times the phase is getting subtracted from 1, and then this is going to get multiplied by the signal, which means we get a downward slope on the square wave. Now this is now our result. And the result itself is getting converted from floating point to fixed point again, and then written into our buffer. This is an idiom in C, or a short way of writing stuff. So the star in here means the content of the address of the buffer here is getting assigned the value of the signal. So you're basically storing that value in that buffer, and then afterwards you are increasing the address of the buffer pointer. Then the phase is going to get incremented by our phase increment. After you are doing your sample, you need to increase the phase by the difference, and then this here basically just computes the. So since this is a float and we are taking the integer of the float, so this means you are getting the integer value of the phase. So if phase is getting above 1, this is returning 1, and then we are subtracting 1 from the phase. So basically this whole thing means add the phase. So if you're at 0.75 and you increase this by 0.5 and then you subtract 1, you get back to 0.5. So this is basically what we call modulo 1. So we will never get out of that range of 0 to 1. And you need to make sure that this is the case. And then we increment the LFO variable by the increment and put the phase that we just computed into the state, and then the LFO into the state after we've written all the pieces into our buffer. And then we return. And that's the complete oscillator for a PWM waveform. Now, there is a need to caution you. This is a so-called naive implementation. Naive implementation means you're just returning a pure waveform. It's like this. It's a -1 and +1. And the edges are very sharp. It's so sharp in here, you don't even see the lines between the 2 points. And sharp edges in digital systems mean aliasing. Aliasing is unwanted frequencies that you get when you are creating sharp edges. And this is not going to sound nicely. And you have to do something about this, but that's the topic of a different part of the series. Okay, thank you for listening to the second part of the video. I know it's been long, but I just wanted to get this out and I hope you could learn something. If there's anything that you need to get explained in more or less depth, please give me a feedback. I'm glad to hear from you guys so I can adapt the series. The series is not scripted. I'm just doing this out of my head. So sorry if there is a lot of jumping around, but that's how it is. In the next part, we will look into the waves oscillator, which is a wavetable oscillator, and see how it works. See you then.